Hello everyone, welcome back again to this online structural geology NPTEL course. We are lecture number 25 and we are actually in the week of Boudinage and related structures. However, this is the second lecture of this week. In the first week we learned something related to called porphyroblast, where we looked at deformation at different stages and how it happens in microstructures, and then how we can relate these sort of things to a large scale deformation and at the same time metamorphisms and so on. I hope you liked that lecture. In this lecture we will start actually the topic of this week, which is Boudinage and related structures, and today we will focus on Boudinage and Pinch-n-Swell structures, which is the part 1 of this lecture series. Now, what we are going to learn in this lecture, the geometric concepts of Boudinage and Pinch-n-Swell structures. Then we will look at that how do these Boudinage structures actually do form in nature. We will see a series of experiments as well, and then we will try to classify the Boudins based on their geometry and kinematics. Now, you see that most of the times when we deal with a particular structure, particularly we dealt with foliation or planar fabrics, then lineation, then we learned fold, and now this time Boudinage. All these topics of structural geology actually include a lot of terminologies, and these terminologies also take a significant part in describing or in defining the classification schemes of these structures. So, Budin is also not an exclusion of these topics. So, we will also see a lot of names, we will see a lot of different geometries and so on, because with these we actually go to the field, try to identify and describe them, and this is very common for all structures and also applicable for Boudinage structures. Now, so the term Boudinage actually was coined by Lohest 1909 to describe the process of formation of a certain type of structures by fragmentation of a sheet of brittle rock, which is sandwiched between layers of ductile rocks. And the structure Lohest first figured out and described from a sandstone bed in the Bastong region of Belgium. I do not know if I have pronounced the name of the area properly, but it spells as Bastogne. So, could be Bastong or something like that. So, in plan view, let us come to the topic, that is on the surface parallel to the stratification plane. If you look at, then he described it this way, that the sandstone beds are separated into enormous cylinders or Boudins aligned side by side, and the fragments are separated by pods of vein quartz. Now, Boudins is a French term that generally describes the sausage, or to be very specific, blood sausages, if you have seen it. So, we will see these structures very soon. And interestingly, in transverse section the fragments are barrel shaped. So, in the if you look at from the top surfaces, it appears like long enormous cylinders, but on the transverse section the fragments are barrel shaped and are aligned in a row. The individual fragments are called Boudins, as we have described already, and the process itself is called Boudinage. The term Boudin means sausage, as we have described, and in making this analogy Lohest emphasized the plan view of the cylindrical Boudins. However, to some people the analogy meant the similarity of cross sectional view of a row of Boudins to a chain of sausages tied one end to another end. Now, most of the time in the field we see Boudinage structures, particularly on transverse section. We hardly see them on the horizontal surfaces. So, we mostly would actually describe most of the Boudinage structures in this lecture and the next lecture, mostly seeing them on the transverse section. What is interesting, this image here in this slide, this is actually the presentation. So, the illustration of the original Boudins in the report of the field meeting that happened in again Bastong of the Society Geologique de Bulgaria. So, it happened in Bulgaria, and this work he presented in 1909. So, this is his drawing, and we will see actually these typical figure that we are seeing here. We will see this later as well, and this is known as gauche boudinage or something like that. We will learn it soon. So, here are some descriptions that we have just learned. So, stretching, necking, and eventually segmentation of a layered body surrounded by a less competent or more deformable matrix developed side by side, sausage shaped bodies, and these are known as budines. And this is a structure, the budines you generally expect in low grade metamorphic rocks, or budines generally do form during low grade metamorphism of the rocks. Now, boudinage, as we have understood so far, that these describes the processes of fragmentation and separation of linear segments produced by extension parallel to the bedding plane and the failure of a brittle or competent layer which is embedded within a ductile or less competent host. Objects such as fossil pebbles and minerals can also be boudinaged. So, in other ways you can think that you need a strong layer which should be sandwiched by relatively weaker layers. And this is actually included the study of boudinage. You will see in few textbooks and also in some study materials that they are included within the topic of lineations, because we see them in as a linear feature in the rock. We will see or learn more about it later. However, boudinage is just not I would say a lineation like we have learned. It is not a typical lineation. It has some interesting characteristics within its structures, within its geometry and shapes. So, therefore, it demands a special attention, and therefore, we have dedicated a week to learn Budin and Pinch-n-Swell structures. Now, boudinage it can range from micro to macro scales. So, you can see them in large scale in the fields, sometimes on the road sections or some mountains, and you also see them under microscope. So, typically you need a strong layer or dike is broken up at regular intervals into a series of elongate and aligned blocks. So, whose profiles in orthogonal to the axis of the budins are the basis for the boudinage. Now, here is the anatomy of the boudinage. I first describe the image, and then we'll talk about the different parts of it. So, what we see here, so this is slightly yellowish blocks here. These are actually less competent layer. Right, and also these gray and then yellow and so on. And then this dark layer, this darker layer, this brown layer is actually your competent layer. We will see soon how did it form, but this is how it looks like. So, this section you are looking at, this particular section is your transverse section. And this is what you are looking at from the top, where you have now you see these large cylinders that Lohest has described. So, this typical direction is known as longitudinal Budin axis. Then the layer which is undergoing boudinage process is the thickness of this layer, we call it thickness. The individual width of these budins in the transverse section are actually the width of the budins. And interestingly, when you have the budins, you have separations. When these layers are separated, then the layers which actually sandwiched the boudinage, they come in to fill the gaps. So, this gap is known as scar or separation or sometimes nodes, and because this is an empty space, we will see it soon, then these things try to fill up or occupy this space, and therefore, it forms a fold like features, but this is not a buckling type of fold, this is kind of bending fold. Now, as we can see, you can also relate it, because this is a deformation related feature. So, you can relate it with the overall strain ellipsoid. So, if I consider this, certainly this was my stretching direction. So, this was the x, and then y I can align it along the longitudinal Budin axis, and this was the compression direction, and then I can refer it as z. So, we will see it later also in the next lecture, that how Boudinage or Boudinage processes are directly related to strain and strain features. So, the Boudinage structure, the fragments occur in a row, so that you can figure out, or you cannot question the fact that about the continuity of a layer before the Boudinage occurred. So, what I mean by this, that these separated blocks that you see now, they must be once upon a time was a continuous layer. So, it in certain areas we find sometimes irregular isolated fragments of a competent rock within an incompetent host. Now, the fragments are occasionally folded, although they are derived from one or more layers. So, the general continuity of a layer therefore cannot be deciphered with certainty by joining these fragments. So, this is a very special case I am talking about, and these are not typically known as Boudinage, but they are called tectonic inclusions or fish rather than Boudinage. So, to more about this slide, so geometry of the Boudinage, as we have seen, or Boudinage structures may be described in terms of the series of structural elements. So, one is we learned the length of the Budin, so which is measured along its longest direction, and the direction is the Budin axis, we have seen it. The width of a Budin is measured in a section transverse to the Budin axis and along a direction parallel to the layering. So, is this one, as we have learnt little before. The thickness of the Budin is the thickness of the layer which has suffered Boudinage. The distance between two adjacent Budins in a transverse section is called separation, or we have seen you can call it gap or scar or node. And in general way, the gap between two Budins may be described as the scar, sometimes also known as node or gap or separation zone, as we have already described all these features. Now, there is one very important part we should remember. So, when we have seen this in an illustration, let us have a look of some real photographs of Boudinage structures. This is one of the classic images. As you can see, the date is 1955, is a photograph from a paper by Hans Ramberg, and you see that this, the black layer is the competent layer, and these are incompetent layers. Okay. And this as well. So, you can clearly see that these fractures are concentrated only in the black layers. Now, these are not separated yet, they are yet to be separated, but this is a very initial stage of a Boudinage process. Now, we see here that this is a photograph from Chotanagpur gneissic complex, and here you clearly see that this must be a continuous layer, isn't it? This black layer, if you consider, this must be a continuous layer, and now they are broken in parts. You can also see it here in the top layer, and it also broken in parts. It got folded a little bit, but we will talk about it later. But this is how you see the Boudinage in the transverse section. So, this is your what you call scar or separation or gap, and this is the width of the Budin, and you can see here that this is somehow going in. You see here this layer which is less competent is trying to flow inside the layer. You will also see here it is trying to flow inside the layer, inside the gap that is being created. So, these are known as your scar folds, as we have seen in the illustration, and these are actually the bending folds. And these places are actually initially open places, and later these places are filled by mostly some fibers, and this could be quartz or calcite or some other minerals, and these are mostly characterized by larger grain size than the grain size you have in the matrix. Okay, this is another image. You see that a series of layers got boudinaged here. This host rock or the matrix is a marble, and then it had some competent layers of pellitic rocks. And what is interesting, you see that here these layers got also a little bit of a rotation here. So, if I try to follow the trend of this, it does not match here. So, there is a little separation. We will talk about this. These are known as asymmetric boudinage. This is not very typical asymmetric boudinage, but yes, this is on the verge of formation of the asymmetric boudinage. We will see about it. But this is an example of boudinage structure, and this is an allanite crystal, this one, these dark things. And you see here again that this is a microscopic image, the width of the image is 7 millimeter, and here you see this allanite crystal is somehow, at least from this image, we see they got fractured along its length, and we see the separations here, we see another separation is happening here, the separation is here as well. We also see in this scale that these scar folds are happening here as well, and we see the scar folds here as well, things are trying to go in. So, this is how you describe the different or you see them in the field or under the microscope, these boudinage layers. Now, there could be another possibility, as we see in this slide, that if you have extension in both directions. So, you are compressing along the z direction, but x and y both are in the extensional field. That means, you are having more or less a flattening type of strands. So, if that happens, that means that if the boudinage takes place in two directions, the individual boudins in plan view may either be equidimensional or more commonly in equidimensional. As you can see here in this illustration, this is mostly equidimensional. So, if you compress it from the top, then it flows in this direction along the y direction, it also flows along the x direction. So, and this compression direction is your z as it is revealed here. So, it would certainly fracture along the x direction or form boudins along the x direction, and it would also form boudin along the y direction. So, now it is very important that if the individual boudins are in equidimensional, the longer direction you can call as boudin axis, but if they are equal in dimension or equidimensional, then it is little difficult. But if necessary, it is possible to distinguish between the longitudinal boudin axis, which we have defined in this case this one, and then the other one would be your transverse boudin axis. And in a similar way, you can also distinguish a transverse separation or scar this way, and you can also figure out what is your longitudinal separation along the longitudinal boudin axis. So, this is how we see the boudinage which is happening in two different directions under the flattening conditions, and these typical type of boudins are known as chocolate tablet boudinage. We will learn more about it in the next lecture, and we will see how with different structural features, particularly with buckle folding, we can have or we can form the chocolate tablet boudinage at particular conditions. Now, this is an example of field photograph of chocolate tablet boudinage. I took it from EGU blogs. So, what we see here, the matrix, as you can see here, these are the matrix. This matrix is actually calcitic or marble, and then you had a dike of dolomite or dolomite vein or dike, and then it got fractured. You can clearly see the trends. So, one trend is like this, as you can see here, and another trend you can figure out is like this. So, almost orthogonally they got separated, and as a result you get this blocky shape, right. So, this is a very typical, or you can figure it out here, the chocolate tablet Boudinage. So, that means it got extension along this direction and also along this direction. Let me put it here, so it would reveal the entire photograph. So, we will see the mechanics of chocolate tablet Boudinage in a different way later, but to give you an impression how do they look like in the field, this is how it is. You can also search in your search engines in the internet, and you can find many more photographs. Now, in a very similar way, when we talk about Boudinage, then another type of structures do appear in the field, and these are known as pinch-and-swell structures. And as I said, that Boudinage we find mostly in lower grade metamorphic rocks, but pinch-and-swell structures are generally observed in higher grade metamorphic rocks. So, in higher grades, sometimes also in unconsolidated rocks. What I mean by saying this, that the competence contrast is less between the layer which would be undergoing Boudinage or pinch-and-swell and the sandwich materials. So, the competent layers have generally not broken through. So, narrow thinned necks separate and alternate with Boudins of relatively still thick layers. The resulting structure is called pinch-and-swell. We will see it soon. After separation, the disconnected layer segments display lens or pillow shaped forms. Extreme stretching reduces necks to very thin and long selvage of the layer connecting variably shaped swells. Now, in Budin we saw that it occurs like this. So, you have real blocks, but in pinch-and-swell, instead of this block they actually do not get separated. What it happens that they form some sort of necks in between. Okay. This you can experiment by yourself by using a straw that we use to generally drink cold drinks and so on. So, these are known as swells and these are known as necks. We will see it in the next slide actually. So, yes, this is how it is. Again, it is the same configuration. We have incompetent layer, incompetent layer, incompetent layer, incompetent layer, incompetent layer, and we have a competent layer here. However, the competence contrast between these incompetent layers and the competent layer in this case is less than what we have seen before. So, if that happens, then again this is your stretching direction x, and instead of fragmenting the competent layer, it forms the pinch-and-swell structure. So, pinch we have understood that this is the pinch and the swallowen part is known as swell. Then instead of width we generally describe it as wavelength, and then this alignment of the neck is known as neckline or swell axis. So, this is how it looks like. You also develop the scar folds along the necks of these pinch-and-swell structures. Now, this is an example of pinch-and-swell structure. It's a diopside amphibolite layer that you can see here, this dark layer, and then material matrix is the marble. But this is how the pinch-and-swell structure looks like in the field, and this is another one. And you see that, so it is not fragmented as we have seen before. It has this swells here and then pinch here, right. Then again a swell and then again a pinch. So, this is alternate calc silicate rock. So, these are the silicate part and this is the calcitic part, and of course, silicates are stronger than the calcite at high grades or at some temperatures, and therefore, the silicates are undergoing pinch-and-swell, whether calcite is working as less competent material or matrix to produce the pinch-and-swell structure. Now, how do they form? What is the origin of this Boudinage structure? Now, people mostly figure out the Boudinage structure or most of the structures that we see in nature by experiments. So, that also happened with the Boudinage. So, Boudinage mostly results from heterogeneous layer parallel extension and disruption of a relatively hard layer or object surrounded by a more ductile matrix. So, this we have been talking several times, but this is how the Boudinages do form. So, you can imagine that if I consider a model, then I have a model. That model essentially needs to have a 3-layer package. So, the middle layer, as we are talking about, is the competent layer, and the upper and lower layers must be less competent layers. Now, the sequence is made such a way that rate at which the middle layer would flow slowly compared to the confining matrix layers. So, that means we will see it next soon, that if I apply a layer normal compression, as you can see here, then this top and bottom layers would flow faster than the layer in between. So, what is happening if that happens? So, if this layer is flowing faster, the rate of strain accumulation in this layer, if it is faster than the layer in the middle, it generates an enormous amount of friction at the boundary. So, whether this red layer here is trying to deform, trying to flow horizontally, but this gray layer at the top and bottom is also trying to pull it away from each other. So, therefore, with a particular condition, at a particular condition, we will see that this interface friction and then the outward flow would produce an extensional stress in the stiff layer. So, therefore, you have some sort of stress going on in this direction, and if that continues, so if the strain rate in the sequence as a whole exceeds the rate at which the stiff layer can behave in ductile manner, then it splits when its strength is exceeded. What I mean by this, that we have generated in the previous slide a significant amount of tensile stress or extensional stress along the layer. So, therefore, it has to break at the middle, and then the force is still there. So, you still have friction continued, and then this separation increases. However, that is not the case that would run forever. What I mean by this, that if this deformation continues, then this block behaves separately, and again this block also has developed an extensional strain within itself, and therefore, it produces another fracture, and same happens here. So, this is how it multiplies and the Boudinage processes go on. Now, one can also form Boudins or pinch-and-swell structures, as you have seen here, that you need a layer normal compression, but when you have the global stress in a compression mode, you also can form a Boudinage structure. We will see later that folds and Boudinages are sometimes closely associated if there are certain conditions. But even in that case, we will see that even the global stress is compressive, but the layers that is undergoing in Boudinage processes have to have a local extension direction along the layer. We will see about it later. Now, so as I said, that the Boudinage structures that we have learned, the origin and so on, this we mostly derived from experiments, and here I would like to show you some of the experiments. So, again the first one is one of the very classic ones from 1955 Ramberg paper. He used plasticine as the competent material in the first panel, and you can see that this is how he is developing with the flow, how he is developing this Boudinage. And the second panel, these white things are his stiff layers, and these are cheese. Okay. and the outside materials in both cases are putty. So, you can also see here that how with this, when the compression went on, he produced Boudinage structure nicely. Now, this is another experiment from Marcos et al., where you see these four are four different experiments. He changed the layer thickness and then deformed it. So, here the layers are actually clay, and the matrix, the less competent matrix, is PDMS, is a kind of polymer, is known as polydimethylsiloxane, and here he also produced, as you can see, that Boudinage structure. People have also produced Boudinage structure numerically. Once you know the rheology and so on, we can produce it with some numerical codes, and this is a work of Abe and Urai published in 2012, as you can see here. This black is a competent rock and the light gray is the matrix, which is incompetent, and here the sequence is like this. So, you can see that, as I was talking about, you just do not stop with one or two Boudinage, you continue multiplying the numbers, and at the end you arrive somewhere like this. The red line here is just a marker, and you see these red lines are here and here developing the scar folds. Now, the Budins in the profile, as we have seen in few cases, that we have pinch and swell structures in one hand. So, it is like lensoid shape, and in few cases in field photographs we have seen the Budins are really straight. So, the Budin profiles are variable, as you can imagine, and we will see later that it can be symmetrical or asymmetrical. The long or exterior faces, usually the layer boundaries of the Budins can be concave, or you can call it bone shaped Budins, it can be convex, you can call it barrel shaped Budins, or parallel to each other, then you call it blocky Budins. I mean, all these terminologies have their own meanings and significances, we will learn about it later. But when you have this concave, convex or parallel Budins, they actually indicate some sort of rheological consequences. The shapes reflect the ductility contrast between the layers and the matrix. So, large contrasts generally tend to produce sharp edges, and small or less contrasts produce rounded Budins. So, here is an example, as you can see here, I just gave 4 examples, we will see more later. So, this is straight, this is convex, this is concave, sometimes it is known as fish mouth, as you can see from this particular shape here, it is like a fish mouth, and then tapering, where the edge is tapering. Here I have given some examples. So, as you can see here, these faces are pretty much straight, also this. So, these are straight faces, these are convex, as you can see here. Then concave or fish mouth, you can see here, this is the shape of the Budin, so on, and then tapering, you can see here, it is exactly like this, and also the next one. Now, these photographs I took from a large image, so I have cropped it, I also rotated them to adjust the shape. Now, classification of Boudinage is something that we have to do, which is one of the aims of this lecture. There are many classification schemes of Boudinage, and again many classification schemes are there, and in a very similar way no classification is complete, but they are classified based on either geometry or kinematics and so on. So, what I will do in this lecture, I will just give you a tour of this with some logical explanations of these classification schemes. The first classification we will learn is symmetric and asymmetric Boudinage. A symmetric Boudinage is when there is no slip along the inter-Budin surfaces. So, the scar or the separation of these Budin spaces did not undergo any slip in between. So, what you see here in this image, that these are pretty much straight. Okay. So, there was no slip along this or anyway. So, these things were absent. So, therefore, these are known as symmetric Boudinage, and sometimes we also call them as no slip Boudinage. Asymmetric Boudinage is exactly the opposite, when you have a slip along the inter-Budin surfaces. And there could be two possibilities, one is antithetic or A-slip type of Boudinage and synthetic or S-type asymmetric Boudinage, and this is with respect to the bulk shear sands. So, in both cases, these two illustrations, the shear was something like that, and as you can see here, within this intra-Boudinage spaces, the shear direction, it went this way and this went this way. So, here the shear sense is dextral, but here it is sinistral. So, it is not matching with the global or bulk shear strength. So, therefore, this is so this is antithetic slip, and then in this case you see that this is the shear sense which is very similar to the global shear sense, and therefore, this is synthetic type of asymmetric Boudinage. Now, there is another classification scheme which is given by Ghosh and Sengupta in 1999, and they classified the Boudinage in 4 ways. One is object Boudinage, then single layer Boudinage, multiple layer Boudinage, and foliation Boudinage. Now, object Boudinages are some sort of a competent object, but of limited dimensional extent. So, you can think of a mineral grain or something like that, very small competent material undergoing Boudinage processes. So, here you can see an example here. So, this is the scale about 1 millimeter, and you see here this is a mica grain which undergone some sort of Boudinage processes. Now, single layer Boudinage is generally you see a competent layer, a single competent layer which is embedded within a less competent host. As you can see here, there is a single competent layer undergoing Boudinage processes here and here. Now, multiple layer Boudinage is a very interesting one, is some sort of a packet of thin competent layers, as you can see here. So, these are some thin competent layers, and they actually get Boudinaged together, and sometimes they call also, they are known also composite Boudinage. So, composite Boudinage is sometimes a variation of multiple layer Boudinage composed of Boudinaged sublayers within a Boudinaged packet of layers, giving nested Boudins of different scale. As you can see here, that this you can consider as a Budin, but it has many other individual Budins. So, therefore, this is a competent Boudinage. And then there is foliation Boudinage. So, sometimes foliated rocks do show Boudinage process, as you can see here, that here we have this Boudinage, and this happens apparently with no competence contrast. So, foliation Boudinage at one point of time was extremely important for researchers. Now, people have understood why do foliation Boudinage happen, but this foliation Boudinage are spectacular to see in the field as well, along with the other types of Boudinage. So, these are the classifications, 4 types: object Boudinage, single layer Boudinage, multiple layer Boudinage, and foliation Boudinage. Let us see another classification scheme. So, this classification scheme is given by Goscombe and Pasquier in 2003, and here they considered both kinematics and geometry. So, kinematics means that how do these Budins form with respect to their displacements and so on, and we have learnt about it when we are learning the symmetric and asymmetric Boudinage. So, they define it as no slip Boudinage or symmetric Boudinage, then antithetic slip Boudinage and synthetic slip Boudinage. So, you can figure out that this is symmetric type as it is written here, and these two actually are asymmetric. Jump to the geometry from the kinematics, then we see that no slip Boudinage are of course symmetric types, antithetic slip Boudinage domino types, and synthetic slip Boudinage shear band types. Now, let us focus on the symmetric types. In symmetric types, we have 2 classes, one is drawn Budins, another is turned Budins. What these are we will see in the next slide. Within the drawn Budins, we have naked Budins and tapering Budins, and within the turned Budins, we have straight face Budins and concave face Budins. In the domino type domain, we have domino Budins and gush Budins. Then within the domino Budins, we have planar domino Budins and dilational domino Budins. Within the gush Budins, we have forked gush Budins and sigmoidal gush Budins. The shear band Budins remain as shear band Budins, it does not have any further classifications within this. Now, let us have a look that what do we mean by all these terms, these drawn Budins, torn Budins, domino Budins, gush Budins and shear band Budins. So, let us start with the domino Budins. Domino Budins are some sort of blocks of asymmetric, usually short, stubby rhomb shapes with angular edges. Now, the domino Budins is now people use it, but it has a legacy of many names and I have listed here few. So, these are also known as tiling structures, bookshelf sliding, sheared stack of cards model, type 1 asymmetric pull aparts, extensional fracture Boudinage and so on. The gush Budins are when the inter-Boudinage space or the scar is dilational and sigmoidal, and it could be either smooth or continuous curved or angular geometry. Now, sometimes these dilational spaces are filled by some other minerals and these are known as, so it is some sort of tensile gashes and therefore, it is known as gush Budins. We will see examples soon. Shear band Budins are asymmetric with rounded rhomb or tapering lens shapes, typically with relatively high aspect ratio, and these are also known as asymmetric Pinch-n-Swell, sigmoidal Boudinage, shear fracture Boudinage and asymmetric extensional structures. Now, drawn and torn Boudinage or Budins, they are little different from this. So, these three the domino, gush and shear band, these are mostly their shapes and geometry together with their kinematics, but drawn and torn these are essentially kinematic things. So, drawn Budins are symmetric Budin with significant ductile stretch and no block rotation. Drawn Budins vary continuously in scar space and degree of thinning of the interconnecting neck zone. You define it in two classes, one is naked and another is tapering Budins. What we have learned, so someone is drawing it, so that means it is like this and then you form it this way. Okay. So, you see these are what I have drawn here, tapering Budin. So, it is a kind of pinch-n-swell structure, but someone is drawing this layer from both ends and therefore, you see the features like this. And torn Budin have the sharp inter-Budin surfaces. So, it is like this and equivalent to the Budin face across which there is significant dilation. So, these are the dilations we can talk about, which is also equivalent to the layer extensions. Now, for strain measurements, torn Budins are much better than drawn Budins. So, we have learned the strain measurements from Budins, but now you can figure out the torn Budins because their layer extension is equivalent to the dilation. So, these are much more useful for strain measurement. Now, here we can see it better that this Budin block geometry. So, shear band type it is like this. So, here the shear sense is again like this and this is the shear sense in the intra Boudinage spaces. These are drawn Budins as we have drawn, these are torn Budins, these are domino Budins, again the shear sense here is like this and this is deforming this way, this is slipping this way, and these are the gush Budins where you see this asymmetric veins are inside the Budins where the shear sense is somehow like this inside the intra Boudinage spaces. You can further classify it in a different way. So, this is another one that you can have the face. So, what we define here that if I have a Budin here like this, then this is known as exterior face and this is known as face, intra-Boudinage face only, okay, or intra-Boudinage face you can call it. Now, based on the curvature of these faces, so whether it is like this or straight, whether IB face or intra-Boudinage face is straight or like this or like this. So, based on this it is possible to classify the Budins in a different way based on their exterior curvature and face curvature. Now, what we see here that theoretically of course many possibilities are there, but these two shapes, this one and this one, are rare, and what is under this light yellow area defined by uncommon, these are also not so much visible in the field, but these which is under the white field, these we see frequently, this fish mouth and so on, we see them commonly. So, it is actually based on that how your exterior face and interior face or inter-Boudinage face, whether it is curved or straight, and if it is curved then whether it is concave or convex. So, based on that people also do classify the Boudinage in this way. Now, with this I finish this lecture. In the next lecture we will continue this and we will see that how we can relate Boudinage structures. So, what is the importance of Boudinage structures when we try to interpret some other structures, for example fold and so on. So, thank you very much. I will see you in the next lecture.